Okay, 4.5 is on graphs of sine and cosine. So we're going to learn the basic waves of these. We'll transform these functions and do some modeling. And this has tons of application. Obviously, there's waves exist in nature, right? With mechanical waves, sound waves, electromagnetic radiation is waves. There's a lot of waves that exist in the real world that are helpful to model, so we can predict some aspects of them. So first of all, a sine can be written in the form like this. This is how we're going to write it in standard form, where A, B, C, and D are constants. Obviously, A is our vertical stretch. B affects our period, or our horizontal stretch. C is going to affect our phase shift, left or right. D is going to affect our shift up or down, vertical shift. Okay, instead of the vertical stretch for A, we're going to call that the amplitude, okay? And it's just the absolute value of this number that's right in front, pretty easy. What the amplitude is it's just how high or low the wave goes relative to the middle of the wave. So if this is 1, which the normal sine and cosine is, then the amplitude is just 1. If this is 3, then the amplitude is 3, and so on. All right, the period of a sine wave is always going to be 2 pi over the absolute value of b. So we won't use negative period, we'll just use positive numbers, so always use a positive b. But that's on our formula sheet, so you're not going to have to memorize that. You will have to use it though. Here's an example then. Let's find the period of this, and let's use a language of transformations to describe how it relates to the original parent function y equals sine of x. So we know the period of the sine function is 2 pi over b. We know in this case that b is 1/2. The number is being multiplied to x. Instead of dividing by 1/2, let's multiply by the reciprocal, 2. 2 pi times 2 gives you 4 pi. So the new period of this function is 4 pi. So the new period is twice as big as the old period. So we know that basically that thing has been horizontally stretched by a factor of 2. So we would say, if the original sine looks like this, the new function is now stretched by a factor of 2. So we could describe that in words. Okay, frequency is the reciprocal of period. So if the period was 2 pi over b, the frequency is going to be the reciprocal of that. So keep in mind the period is always the reciprocal of frequency. So what the frequency is, the number of complete cycles a wave completes in a unit interval. Typically that unit interval is measured in time, and typically that's 1 second. So frequency is usually measured in hertz as the unit, which is the number of cycles per second. So we can look at sound waves, we can look at light waves, different radio waves, and we can talk about how many cycles they make per second as the frequency of that wave. Okay, so here's another example then. This is a period change and a phase shift. So let's construct a sine. We know our sine functions are a sine of bx plus c plus d. We know this has an amplitude of 4, so we can plug in 4. We know the new period is going to be pi over 3, so if we compare that, period is equal to 2 pi over b. And it needs to be pi over 3, so we can find out what b would have to be in order to get that. So I would flip both sides probably, and then multiply by 2 pi. And if I do that, the pi's cancel, and you get 6, so b equals 6. So this would be 6x plus c plus d. Now this thing says it has a phase shift, but does not have a period change. I'm sorry, it says it has a phase shift and a period change, but it doesn't say it's been shifted up or down at all. So, and it hasn't because it goes through the point 2, 0. So there's going to be no d, there's going to be no vertical shift. What we can do now is use the order pair that they gave us to find c. So if we plug in 0 for y, and if we plug in 6 for x, or I'm sorry, 2 for x, we can then find c. So divide both sides by 4, you get 0 equals the sine of 12 plus c. Well, on a unit circle, if you want to look at where this would be, c would have to be negative 12, because we know the sine of 0 is 0, so we want to make sure that, whatever we subtract here gives you sine of 0 so that we get 0. So c is negative 12, which makes our function y equals 4 sine of 6x minus 12. Another way to look at this is you can factor out a 6 from here, and you end up with x minus 2. which makes sense because if it goes through 2, 0, the regular sine function looks like this, where it starts off at 0, and the new sine function has been shifted over so it goes through 2, 0, so it's been shifted over 2 units to the right, which is exactly what this transformation says. If we pull up the 6 there and isolate what we're doing to x. So there's our function right there that has the given transformations. Okay, one more example then. Let's say we have this function here, and we want to sketch the graph of it. If you really want to get good at this stuff, try it about a calculator based on the transformations you know about. That's really, really good practice, and it's pretty challenging actually. So what I do is I graph this by hand. I will put, if you look at the unit circle, we want to do pi, 90, 180, and 270. So that'd be 90, 180, 270, and then 2 pi, 360. And then do the same thing back the other way. Negative pi over 2, negative pi, negative 270, and negative 2 pi. So sketching a graph, the cosine is really easy then because the cosine starts off here at its highest value of 1, it's the x value. So if this is, we'll make this 1, make this negative 1. So we start off here, and then at 90 degrees it goes to 0. At pi it goes back to negative x value, so negative 1. Then it goes back to 0, and it goes back to positive 1. So if you just follow that pattern, it's pretty easy to graph what the cosine looks like. This wave here. Okay. Now, this other function here has been shrunk by 1/3 because the amplitude is only 1/3, so we're going to only go up to 1/3. It's also been reflected, so it's going to start off down here, but then it's also been shrunk. So we know this point's there, negative 1/3, but it's been shrunk, and how much it's been shrunk you can look at is the period. The period is 2 pi over b, so in this case it's 2 pi over 5, so it's been shrunk down 1/5. So it's going to reach its full cycle in 2 pi over 5, so find 2 pi over 5 on here. So, imagine 1/5 of this whole thing, which is actually somewhere around here, because pi over 2 is 1.57, and 2 pi over 5 is like 1.25. So it's actually going to do, this whole thing in this interval. So I'll just draw a rough sketch. It's going to end up back at its highest point here, which would actually be its lowest point. So it's got to be the reflection image of this, which I know is a little hard. Goes down and then back up, so this will go up and then back down. And the same thing here, it reaches its lowest point again, must be, so it goes up and back down. So that's tricky to do without a calculator, but it's really good practice for everything we talked about as far as function transformations and then all the new stuff we're learning about period of these trig functions. So here's the window they wanted to. They wanted from negative 2 pi. This value is right here, 2 pi over 5, and this one's negative 2 pi over 5. So this is the window they wanted you to graph that in right there. So we just did that by hand. All right, so just to recap then, the amplitude is going to be the absolute value of A, period is going to be 2 pi over B, and the frequency is going to be the reciprocal of the period. All right, let's try some practice problems in the homework and hope this helps.